Okay, for today, we're going to go through work energy power. So this is a relatively easier chapter, I guess, because we have been covering this since Sec 2. And I guess really in this case here, energy is not something too foreign to everybody. Yeah? So let's start now. Okay, so chapter 6, work energy power. Let's just jump straight into it. So 6.1, we're going to start off with that. Okay, so in 6.1, we're going to learn how to identify different forms of energy. And then we're going to state the principle of conservation of energy and use it to solve problems. Okay, so first thing, back to basics. So what is energy? Energy is the capacity to do work. So just like how we always mention that, when we tell you to do something, you say, I got no more energy left. So really energy is the ability or the capacity to do work. You need energy in order to do work. The SI unit is joules. Okay, joule. Joule. Okay, capital J. Now, why is unit so important? Because actually by knowing the unit, it will also help you to identify the quantities in the question. Okay, so I say again, by knowing the unit, it will help you to be able to identify the quantity easier in the question itself. Okay, so what are the different forms of energy? First one, kinetic energy. So anything that is moving, so anything that's moving, it has kinetic energy. So kinetic energy is sort of like the energy of moving objects. Okay, so that's kinetic energy. Potential energy just means stored energy. So there are different forms of stored energy. Okay, so I say again, potential energy means stored energy. So there are different forms of stored energy. First one is chemical potential. So food has, fuel has, all these have chemical potential energy. So the energy is stored in the chemical form. Okay. Batteries also is an example of a chemical potential energy. Okay. Now, another one is the elastic potential energy. So anything that's stretchable. Okay. Stretchable. So a rubber band, a bow that you can pull, all these contain elastic potential energy. So things that are elastic. The one that you are very familiar with is actually gravitational potential energy. I know some of you say gravity, okay, but actually instead of just saying potential energy, instead of just saying gravity, actually the whole idea is that this is what we call GPE, the gravitational potential energy. So it is the energy stored in an object due to its height from the ground. So as long as anything is above, okay, as long as it's above the ground level, it actually has what we call gravitational potential energy. Okay, so these are the various forms of energy that we are familiar with. The other few, we also have electrical energy, light energy, thermal energy, okay, nuclear energy. You realize that for thermal, light, and electrical, we study quite a fair bit of details. Okay, so these are just the other various forms of energy. But in terms of calculation, okay, in this chapter, work energy power, key idea here, you need to learn how to calculate KE, GPE, and work done, okay, which we'll cover later. So those are the various forms of energy. Okay, why we need to know them is because we need to know how to identify. So to identify what are the various forms of energy, you first need to know what are the various forms. So to be able to identify, you know what the forms are. Okay, so that's why they went through like a few pages of it, just to elaborate a little bit more on what the various forms of energy are. Okay, really about some of the principles you need to think about when you're looking at energy conversion. Okay, so what are some of the key principles here? So although it's one big sentence here, but I can break it down in a few parts. First part, when you talk about the principle of conservation energy, it says that energy cannot be created or destroyed. This is the first point you need to mention. Second thing, it can be converted from one form to another. So example, chemical potential energy to the electrical energy, just like battery to the electrical circuit. Okay, and the last one, the total energy in an isolated system is constant. Now, this third point, okay, in terms of how we normally would apply it, it's actually just simply saying that energy before conversion must be equals to energy after conversion. Okay, so these are the three main points that we normally would use when we talk about principle of conservation of energy. Okay, so the energy before conversion and the energy after conversion must be the same. So example, okay, some example of energy conversions are, it's not really applying the principle here, but just sort of like saying what are the possible energy conversion. So first one, you raise a hammer, because you raised it up, it has GPE. When you start to slam it down, because it is moving downwards, the GPE is actually converted to kinetic energy. And once you strike it in, the nail moves in. So the nail moving in, we consider it as work. So the driving the nail into the wooden block, we consider this as work done. So in actual fact, it is like GPE converted to KE, and it's being converted to work done. Alright, so this is the conversion that's seen here. Burning of fossil fuel, I'll let you read it. So being able to talk about what are the energy conversions, you need to be able to do that, because it actually also comes out in your TYS, in your O-level questions also. Not that often, but it does come out. So you must be able to state. Okay, so in terms of the principle of conservation of energy, so we're going to see it in terms of ideal pendulum. Okay, you look at the word, there's the word ideal here. So generally, a pendulum, you let it swing, it actually doesn't follow the principle. It doesn't really like sort of, in the ideal case, right, the thing will just keep swinging non-stop. That's the ideal case. But of course, in real life, you know that when you swing a pendulum, you'll ultimately come to stop. You will not keep swinging non-stop. Okay, so we're going to look at this a little bit. Okay, so for how do we apply POCO, principle of conservation of energy, to this? So first one, your pendulum is down here. I raised it up. So you can see, because it's raised to a height of X, okay, this is the amount of GPE. You can say that it has been raised to this amount of GPE. Once you let it swing, it goes down. At this current point, at its lowest point, okay, we can say that it has the maximum KE. Then, so GPE, as it swings down, it will convert to KE. Once it reaches this lowest point, it will swing back up. When it swings back up, the K is being lost, and it will go back to the same height as before. Then this is also where this is at its GPE. Right? Maximum GPE again. Now, I'm going to just run through the text above. So, the pendulum bob initially is displaced to a height X above the ground. So it gains GPE, okay, because it is above the original position. So when it's being released, swinging downwards, the GPE is actually converted to KE. So think of this, the GPE is converted to KE because it is coming down. The GPE is lost. The object moves faster and faster. That's why KE is gained. Applying the principle of conservation of energy, since energy cannot be created or destroyed, therefore the GPE lost must be equals to the KE gain. So I say again now, because energy cannot be created or destroyed, that's the principle of conservation of energy. It means that whatever GPE that's lost, because you can see the pendulum bob is getting lower and lower and lower, so GPE is lost over here, the GPE loss must be converted to KE gain. And what we realize is that the pendulum bob will reach its lowest point, that means lowest GPE at this particular point. Since it's at its lowest GPE, it must be at its maximum KE, because it will have the most amount of GPE converted to KE. Okay, so I say again, at the lowest point, that's also where it has the lowest amount of GPE. That will be the point where it has this maximum KE. So once it reaches the bottom position, okay, it will actually swing to the other side, and the KE will be converted back to the gravitational potential energy. Okay, KE converted back to GPE. Now, the GPE gain is converted from the KE loss. So you can see once again, we are applying that energy cannot be created or destroyed. We talk about energy can be converted from one form to another. Then we say that, when it reaches the maximum height, it only has GPE because the ball will temporarily come to a stop. Okay, so when it temporarily come to a stop, the speed is 0. That's why its K is 0. Okay, so at this point, when it's at the maximum height, the KE actually is 0. So just take note of that. Then, once it's here, it will come back down again. So the whole process will continue again. So this is the ideal pendulum of it swinging and how the energy is being converted. But in real life, we know that this is the case. Okay, you raise it up to X, as it swings over, it will come to a point where the height is actually lower. Okay, it will not swing back to the original height. So why is it so? I think I need you all to take note of this. Okay, it is because some of the energy is converted to thermal energy. Why thermal energy? Because of frictional forces. What is this frictional forces? It's actually air resistance. Friction with air. Now, so every time when an object experiences friction, okay, heat will be generated. I say another thing, note of this. When friction is experienced by an object, so when friction is experienced, okay, heat is generated. That's why there's thermal energy. So if you don't believe me, you can just very simple exercise. You can just take your two hands, you just place them together, and then you just keep rubbing it. You'll feel that your hand is getting warmer. Okay, because your two hands, when they're rubbing it, you're actually causing it to experience friction. By experiencing friction, you're actually generating heat. Okay, so the GPE is converted to KE, but at the same time, it's also converted to the heat. Okay, so energy is being lost as heat along the process. So that's why ultimately when the K is converted back to GPE, it is of a lower height. Now, then the question is, GPE, KE, they don't go back to original height. So does it mean that we don't, the principle of conservation of energy is not followed? The answer is, it's actually still following the principle of conservation of energy, because at this point, it is GPE. At this point, it is KE plus thermal. At this point, your K is converted, so it becomes GPE plus thermal. So you can see here the thermal energy that is generated from the friction is calculated in. So actually what you can realize is this, is that the total GP at the start. So GPE at start is actually equals to at the middle point, the KE plus the thermal energy, which is then converted to the GPE plus the thermal. So you can see the energy before, energy in the middle, energy at the end is the same throughout the whole system. So it still follows the principle of conservation of energy. Energy is not created or destroyed. It's actually converted from one form to another. And ultimately, the total energy before and after conversion for each of the phases is still the same. Okay? So that's how the principle of conservation is applied in this scenario. When you read out all these examples here, it gives you a little bit more detail on how to do that kind of explanation type of questions. So do take note of it. Okay, I just want to highlight, whenever you see explanation type of questions, do take some time to read through, okay? Because for my combined science students, you may be good at calculation, but explanation tends to be a nightmare for many of you because you do not know how to phrase your answer. So this actually gives a very good way of learning how to phrase it. Okay, so just take note of it. Okay, so key ideas for 6.1. Okay, so we learned that energy is the capacity to do work. Okay, got many forms. Energy can be converted from one form to another. And where do we see this? We see in the principle of conservation of energy. Okay, so take note of this. So that's what we have gone through in 6.1. Now let's go on to 6.2. In 6.2, we're going to learn all the formulas here. We're going to learn the formula for work done, kinetic energy, gravitational potential energy. Now, I just want to highlight one thing. Work done, KE, GPE. These three, I would like to summarize it as their energy. So if they are all energy, what do you think is their units? Their SI unit would be joule. Okay, so most people can understand KE and GPE, yeah lah, joule lah. But what's the units for work done? So most people don't understand that work done is a form of energy, and because it's a form of energy, the units is joule. So when you calculate work done, then all of you scratch head thinking what's the units, right? So just be able to classify them all together. And once you understand that there are different forms of energy, you also know that they can be interconverting from one to another. But why can they convert from one to another? Because you can apply the principle of conservation of energy on them. Alright, POCO in short. Okay, now, so let's go into details for each one of them now. Okay, question figure 6.8, are both the boy and the lady doing work? So we're going to look more into detail for each of this. Now, work is done only when an object moves. So the object must be moving under the influence of a force. So take note, condition is it must move and there must be a force. Okay, condition, these two. So for work to be done, you must make sure that the object moves and the force is applied. So if you look at this scenario here, you can see the tree remains stationary because the tree did not move. This boy, no work done. For this lady, the stroller is moving in the presence of a force. So that's why this one, yes, to work done. Okay. Now let's go into details. So work done by a constant force on an object is the product of a force. So most of you are very familiar with work done equals to force multiplied by distance. I just want to highlight one thing. The distance needs to be in the direction of the force. Okay, you must always remember that the work done must be in the the distance moved must be in the direction of the force. Okay. Now work done units is joule, capital J. This is force, units is in Newton. So take note of it. Last one, the distance that you should be using is actually in meters. So take note of the units there. Okay, so in joules, in Newton, in meters. Now, I want you all to look at this example here. Okay, two students in the library not doing work. Why is this not doing work? So although force is present, so it's a good thing. There's a force, but no distance moved. Therefore, no work done. I think this one quite clear cut, because if work done equals to force times distance, if the distance is 0, anything times 0 equals to 0, right? That's why the work done is 0 in this case here. But for this one, it's a little bit complex, right? A bit more complex. So force is present. Okay, actually there is distance moved. Distance moved have. However, when you take note of this, the force is upwards. Then my question to you is the distance move upwards? Remember I mentioned, right? The distance traveled must be in the direction of the force. And since the force is upwards, but the distance move is not upwards, okay, not upwards. Therefore, we will say that although a force is present, but distance is not in direction of force. So our distance moved is not in direction of the force. So because of that, we will take it that WD equals to force times distance. Since it's not in direction of the force, actually the distance traveled in the direction of force is 0. As such, the work done is also 0. Okay, these kind of cases, I need you to take note of it because they like to come out in MCQ. So be aware of how to go about evaluating this. Okay, so the explanation a little bit more is here. So do take note of it. Okay, so how is work related to energy and force? So you need energy to do work. And for you to do work, you need to make sure that object move and there must be a force present. That's why the formula is work done equals to force times distance. Okay, so this one no issue now. Then the next question is, how is work done related to kinetic energy? So a force needs to be applied to make a stationary object move. So if you apply a force and the object moves, see, force applied, object move, there is work done. And when the object starts to move, you realize, object that moves have what kind of energy? It has kinetic energy. So actually, when you do work and when there's work done and the object actually starts moving or moves faster, okay, what's happening is that you're actually causing a change in the KE. Okay, so hence an object gains KE because work done on it, because of the work done on it by a force. So question is how to calculate KE. I think by now you're more or less quite familiar already. So you can see here they put EK, but I think most of you normally will write this. Equals to half mv squared. Okay, so do take note of the square here. V represents velocity, okay, or the speed of the body. The units must be in meters per second. So please take note. The mass here must be in kilograms. So units are important because if you put in the wrong units, you will not have the correct value for the kinetic energy. Okay, so for the kinetic energy here, the units is in joules. Okay, knowing the units, I think very important. So I just need to take note from the equation. Same, if you have a two object, same mass. So m is the same, right? But they are moving at different speed. So the higher the speed, the greater the KE. So faster object obviously have higher KE. I think this one clear cut. Next one, if the object have the same speed, but they have different mass. So we know that the object with a greater mass will have a greater KE. So just take note of this also. Okay, this is more of a qualitative, that means more of a like explanation type of questions. So this will be very useful, okay, because you realize what we are trying to say is keeping something constant when one of them is higher, it causes a K difference. So we are actually using the formula here to evaluate. Okay, when one of the variable is constant, then what happens when the other thing is higher? So look at this. So imagine m is constant. Then when V increase, KE increase. That's for whatever I'm drawing here is actually for this part. Okay, so let me erase. I make it clearer for you all. So what this thing here is saying is that if I compare KE equals to half mv squared, if the m stays constant, okay, then the V increase. So if m stay constant and V increase, what you want to realize is that because it's m times v squared, right? So if m stays constant, v increase, KE will increase. For the second part, what they're trying to say here is this. I got KE equals to half mv squared. When the v remains constant, okay, when the v remains constant, but the m increase, okay, m increase. So V constant, M increase, this is going to cause the KE also to increase. So learn how to be able to understand the relationship using the formula here. Okay, calculation, quite a few examples here, so do take note of it. You realize they even help you convert, so you can do take note here how to convert km per hour to meter per second. So these are good examples here to just let you have an understanding of how you can use the formulas and what are the things you need to take note when using them. Okay, so that's for KE. Next one we're going to go into is gravitational potential energy, GPE. So GPE, as mentioned, is that anything that is above the ground, okay, anything that's above the ground level, you will possess GPE. Okay, so what's the formula that we're going to apply here? So most of you will not write this, most of you will write GPE equals to mgh. So GPE is the gravitational potential energy because it's a form of energy. The units obviously will be joule. M represents mass, so it must be in kilogram. Kg. G, I think most of you know, is you all call it gravity or gravitational acceleration or gravitational field strength. So this is normally in meter per second square or Newton per kg. Most of us recognize that G normally will have a value of 10. Last one, H. H is height. Height is obviously in meters. Okay. So do take note of the units, because once again, if you plug the units in wrongly, you can't get the correct energy calculation. Okay, so any object that has a certain height above the ground, okay, it will possess GPE. So do take note of that. So these are just some additional examples on how to calculate. So you can see the purpose you use 10 grams, so you need to convert to kg. So all the things, little things that I've been mentioning that you need to take note of, the questions here actually do cover them quite a fair bit. Of course, I know you all seldom use a textbook, so please make sure, as I mentioned all this, glance through it, look through it, take note of the little examples. Okay. 6.5, I think this is an example of Poco. Poco in relation to KE. Okay, and work done. So it's quite a good example here. Okay, and then I think there's also GPE mentioned at the later part. So most questions actually have all three parts in it. So in order for you to be able to understand how all this conversion works, my simple take on this is always, don't jump straight into the question. Read through it carefully, understand, try to picture it, imagine what's happening in that situation here. Okay, so you realize they purposely will draw the diagram out. Not every time diagram is given to you, so if need be, you can draw the diagram on your own. Okay, so I will not go through these examples, it's for you to look through. Okay, so anyway, yeah, so just a wrap up for 6.2. So we mentioned work done. Okay, so we mentioned work done. We went to details of what it is. Then the formula we mentioned, work done is force times distance. This S is actually distance, so just take note of it. Okay, we went through the example of no work done. Then we went through formulas for half mv square for KE. Went through the formula for GPE and what GPE is. Now, for this part over here, actually what you realize is that they are just applying Poco. Okay, I say again, they are just applying Poco. Okay, so I just need to take note for a pendulum or free falling object. Okay, this one important. I say again, for pendulum or free falling object, the maximum amount of GPE, so the max amount of GPE, okay, will be converted to the maximum amount of KE. Right, because as the object is falling down, okay, I say it, as the object is falling, the GPE is converted to KE. When all the GPE is converted to KE, I say now, when all the GPE is converted to KE, that will be the point where it's at its lowest. And because all the GPE is converted to KE, the point where it is having its lowest GPE is also the point where it's having its maximum KE. And because of that kind of a conclusion, we can always equate this thing, that the maximum amount of GPE, when it's converted to KE, it will actually gives you the maximum of KE. Okay, so I say again, I repeat, the maximum amount of KE, the value of it will actually also be equal to the maximum amount of KE. Okay, so just take note of this. You will need to apply to this in quite a few situations in your TYS also. So just take note. Okay, examples all here, I think you can go through it. The last part of work energy is actually on power. So what exactly is power? So before we go into the definition and stuff, I want us to look at these scenarios. I think the scenarios put it very nicely. So imagine boy A and boy B, they start off at the bottom. Okay, boy A and boy B start off at the bottom. So they have equal mass. Now, boy A reached the 4th story before boy B. Okay, boy A reached the 4th story before boy B. So boy A was faster, right? Since they have equal mass, they travel the same distance, because from the bottom to the top, okay, they did the same amount of work. So the energy consumed is the same. Okay, the energy consumed is the same for the boys to move from the bottom to the top. However, since boy A took a shorter time, okay, we can say that boy A has more power. Now you can just think about it. Same amount of energy, but I take lesser time. Obviously, this boy will be more powerful in that sense, right? Okay. Scenario 2. Boy A has a larger mass than boy B. Okay, but they both reach the fourth story at the same time. So now, since boy A has a larger mass, he needs to do more work. So this time around, the energy is different, The energy is different because boy A has a larger mass. Although the distance traveled is the same, it's 4 stories, but we know that when you have a heavier mass, you will need to do more work for the same amount of distance. As such, because we know that boy A does more work than boy B, but the time used is the same, we can say that boy A is more powerful. Okay, he uses more energy per unit time. So therefore, as such, power is defined as the rate of work done or rate of energy conversion. Another way of looking at it, I would like to say is that it's also equals to the work done per unit time. Okay, if I can do more work per second, or per unit time, then generally we use per second. So if I can do more work per second, it's taken that you have a higher power. Okay, so I say again, if you do more work per second, you are also considered to have a higher power. So in the formula equation form, you will see this. Generally, I will use P equals to E over T. Okay, I don't really like use the work done because work done is a form of energy, just might as well use energy, right? So this is power. Power, the units is watt, right, capital W. Energy, obviously we all know now, is joule, capital J. Time here, do take note, is very important. You must use the correct units for time. The time here must be in seconds. You use the wrong units, I'm sorry, once again, your calculation will be wrong. So power is about how much energy is done per unit time. So if I can do more work in lesser amount of time, I will be considered having more power. Okay? So these are just some additional examples to just think through it, okay, on how to calculate power. Some additional examples. So do look through them. Okay, I will not go through the examples itself because I think they're quite straightforward. Okay, main idea, of course, once I've gone through all this, you need to go through your TYS to just get more practice. Okay, look through these questions just to internalize it. Okay, so in key idea for here, for this last part on 6.3 is that the work done is the rate, the power is the rate of work done, or as I mentioned just now, is the work done per unit time. Okay, the unit for power is watt. So 100 watts, just a conclusion, 100 watt, it means that it uses 100 joules every second. Something that is 200 watts, it means that it uses 200 joule every second. So a light bulb, if the power is very high, like for example 20 watt, 30 watt, 40 watt, compared to a LED light which could be 5 watt, you can imagine how much energy is used per second for that kind of light. Okay, so I hope this gives you a deeper understanding, deeper appreciation of how you can possibly look at all this and calculate which one uses more energy and how we can conserve energy for the future. Okay, so that's all from me. Under Map It is a very good summary of everything else. Okay, I will not go through it anymore. Okay, because whatever I went through in the key ideas is all captured here. Okay, so really that's all for today. Once again, apologies for the keep on hanging. Okay, so that's all from me. If you've got no questions, you can leave now. Okay, I'll stop recording the session really.